Hello, I'm Sam, if you don't know me, or you likely do know me, in which case no introduction is necessary. I'm explaining number 12 on the Webassign. We have the diagram, which you may have seen already since it is on the Webassign. And you also might have noticed that it looks like the energy of activation forward plus the change in G standard equals the energy of activation reverse. Well, that's not the case, and if you use that formula, everything gets messed up. That's what I did the first time, and why I was so confused. Turns out these are actually vectors. The energy of activation are up vectors, because they tell you how much energy it takes to overcome the necessary steps and get to the final products of your reaction. So really they're up. Change in G standard, by contrast, is down vector, because it's really telling you how far the G falls throughout the course of the reaction. Another way to think of it is your change in G in this sort of situation is going to be negative, but your energy of activations are both positive, so we have to get to a negative from some positives. So that means we have to subtract the bigger one from the smaller one to get the negative. You can also do it with vectors like I did, showing that this points up. You subtract that one, and subtracting the vector is basically like pointing it in the opposite direction, and then you start it at the top, and the final vector you would get in that situation is this one. So really, in conclusion, from this part anyway, the energy of activation forward minus the energy of activation reverse equals the change in G. And you can see that, as I have written it, here. Yes. We also know that the standard change in G equals negative RT times the natural log of K. So that means we can set that equal to the whole thing and just focus on this little equation for now. So now we divide both sides by negative RT and then raise them to the E to get rid of the natural log. So then we have K equals E to the energy of activation forward minus the energy of activation reverse divided by negative RT. Well, take that negative and apply it to the top, and we get E to the energy of activation reverse minus the energy of activation forward over RT. Now we need the Arrhenius equation. So here's K sub F equals AE to the negative energy of activation forward over RT, and K sub R equals the same thing, but with the energy of activation for being reverse. And we're trying to prove that K equals K sub F over K sub R. So that means it's that divided by that. So you take this section of the equation and divide it by that section of the equation, and that's what I did over here. And the A's will cancel, because it's just A divided by A. The E's don't cancel though, because they have two different exponents. So you have to subtract the exponents, subtract the bottom from the top, and then you'll get that over here, rearrange it just a little bit, and you'll find that it is the exact same thing we wrote down here. So that means that Kf over Kr, following this path, equals K. Alright. So therefore, K equals Kf over Kr at equilibrium. And the reason why it's at equilibrium is because this formula is only really designed for when things are at equilibrium. Hope that clears things up. Have a nice day.